All right, so hello, and welcome everybody to this beautiful platform PW. This is your physics mentor Gaurav Tiwari, and today, my dear kids, we'll be learning the first chapter of grade 11th CBSE physics, which is units and measurement, right? But before we do any of that, just quickly let me know if I'm clearly audible and visible or not. Hello, everybody. Just let me know if I'm clearly audible and visible to everybody. Hello. Hello, Devansh. Hello, Moody Man. Hello, Cookie. Okay, so these names are very different than the actual names, by the way. So yeah, so we are going to start with units and measurement, right, beta? Okay. So all of this discussion that we are going to do, right, primarily, talks about your concepts, right, and everything that you will see in the class, right, primarily focuses on all the concepts. So here I have the Vernier caliper as well, right? So with the help of this, we will learn how this Vernier caliper is, used, right? And how do we take the measurements from it, right? So there are different things that we have, right? And this is going to be a very conceptual lecture, right? This is going to be a very conceptual lecture, right? Okay. Okay, this is my real name. Okay. Hi, Somesh, right? So my dear kids, yeah, so if I'm clearly audible and visible, just give me a quick yes. We will start right away with the concepts. My dear kids, if you talk about NEET exam, if you talk about JEE exam, right, in all these exams, this chapter can give you 4 easy marks, right? Okay. And by the way, there are smart kids, right? They use the principles that they have understood in this particular chapter, and they apply in the concepts of the questions of other chapters as well, right? Many times, just to select the right option, the concepts of this chapter are very, very useful. Okay. Shall we start? Okay. So what about a screw gauge? A screw gauge will be there as well. Yeah, screw gauge is also there, right? So we will talk about everything. Okay. All right. So Nasir Chipa, Nasir beta, look at the name of the channel. He is saying that Hindi. Okay, I can teach you in Hindi as well. I like the language. It's my mother tongue. But the thing is, this channel is not in Hindi. Just read it. Name of the channel is English Medium, right? So there are other awesome channels. You can watch the lecture over there in Hindi. Okay, beta. So let's start. Let's start this particular channel. If you guys are ready, just give me a quick yes. We will start right away, right? If you guys are ready, just give me a quick yes. We will start right away. Okay. Okay, so we are going to cover everything. We will start with error analysis, right? Then after we will start with dimensional analysis, right? Application of dimensional analysis is also covered in this part, right? And then we will start with Vernier caliper. And one kid was asking, sir, are we going to cover a screw gauge? Yes, that is also there. Significant figure is also there. And finally, mathematical tools. So that part is not going to be covered today, but these are the parts that we are going to talk about in this particular class, right? So we will be talking about all these parts in this particular lecture, right? So yeah, so there are small topics, but lots and lots of topics will be there. Yep. Upload notes. So notes will be uploaded very soon. Okay. Of course, right? So all the concepts will be covered, and they are going to be relevant for all the exams, be it JEE or be it NEET. Okay. So let's start, right? Nishant, very good. So let's start right away with the first thing, error analysis. The first thing is error analysis. My dear kids, right? In the chapter or in the concept of error analysis, 3 things you have to understand. Error of measurement, right? Different types of errors, and then combination of error, right? These are the things that you have to talk about, and we will talk about them in a step-by-step manner, okay? So we are not going to rush anything. We have plenty of time to cover each topic, and all of them are very easy. Only those kids who are going to rush it will find it difficult. So we are not going to rush it, right? So any problem you have, you ask me in the chat, and I'm happy to answer you, right? So let's start right away. The first thing is error of measurement. Error of measurement. So my dear kid, what is happening? Let's say that I go to a shop, right, and I buy some stuff. For example, I go to a shop and I buy this particular box, right? And on the top of the box, it is written the length of the ingredients inside it. So what is there inside? Inside I have a battery of a drone. Okay, this is the drone battery, right? And on top of it, it is written the length of this thing, because if I'm designing a drone, I must know what is the length of all the parts, right? So that I can make the proper arrangement to fit all those parts, right? So the length of the part is written on it is 20.1 centimeter. What is written? 20.1 centimeter. This is the manufacturer writing it, right? On top of it. But when I used my scale and I measured it with the help of my scale, right, and I found it, the value that I took while measuring myself, I got the value 20.2 centimeter. All right. So my dear kid, this was the value, that was the actual value, true value of the measurement, right? And this is the measurement that I took from my measuring tool, right? So can I say that the measurement I took is different from the true value? So clearly there is an error. While I am going to design my drone and I will fit this battery, there will be an error because of my measurement, right? And that is how we could talk about the error of measurement. Error, or how much error I have encountered, clearly the difference between these two. My dear kid, this value is called as true value, all right? And this value is called as measured value, all right? Okay. So the difference between the true value and the measured value, so it is, just take the difference, 20.2 and 20.1. 0.1 difference is there. So that difference is the error in the measurement that we are taking, right? That difference is the error of measurement we are taking, right? Okay. Is that clear? All right. So what is error? So read it. The difference between the true value and the measured value of a quantity is called as error of measurement, right? Let's take another example. Here I have this this thing, right? This rubber, okay? Let's imagine I can make so many things out of it, right? We can make so many things out of it. And let's say the original length of this thing, the true length of this thing is 20 centimeter. And when I measured it 19.8 centimeter. So what was the error in it? Write in the chat box. The true value was 20 centimeter and I measured it with the help of my scale and it turns out to be 19.8 centimeter. So how much error I got? We can say the error of measurement is the true value 20 centimeter minus the measured value, which is 19.8. So that is 0.2 centimeter, right? Is that clear? Hi Ansh. Okay. Is that clear, Vishal? Okay. So let's start. Let's talk about the different types of error. So these are the different types of errors, right? So we have absolute error, mean absolute error, relative error, and percentage error, right? These are the different types of error we have, right? Very good. These are the different types of error we have. What are the different types of errors? We have absolute error, mean absolute error, relative error or fractional error, and percentage error. Out of them, we will be using this one and this one again and again, right? In all upcoming chapters, you will be using them, right? You will be using relative error every time. You will be using percentage error every time. So just pay a close attention because we are going to understand something very simple and very important, right? So it is the absolute error first, right? So now understand that absolute error is simply the difference between the true value and the measured value, right? Let's say the true value of a quantity was 20 centimeter, right? The first guy, let's say 4 kids are measuring the same thing, right? This was a 20 centimeter long rod, right? 20 centimeter long rod, and 4 kids are measuring it, right? First kid is measuring 20.1 centimeter. Second kid is measuring 20.2 centimeter. Third kid is measuring 19.9 centimeter, right? And fourth kid is measuring 19.8 centimeter. So you see that we can say all the measurements are off from the true value. They are not exact the true value. They are slightly different from the true value. Yes or no? All the measurements are not exactly the same, right? They are slightly different from the true value. So we can say that what is the absolute error in the first measurement? What is the absolute error in the first measurement, right? So we can say that, read it, absolute error in the measurement of physical quantity is the magnitude of the difference between true value, this is the true value, right, which is given to you 20.0 centimeter, and the measured value. So let's say that this is Mayank is measuring it and he said that my measurement, sir, is 20.1. Let us say another kid is also there, right? Let's take one of your name, Nishant. Nishant is measuring, right? He is saying, sir, my measurement of the same thing is 20.2 centimeter. Let's take another name from Pinky. Okay, so third kid is Pinky. She is saying, sir, my measurement of the same object is 19.9 centimeter. So the fourth kid is saying that. Fourth kid, who wants to come up? Suzanne, right? The fourth kid is Suzanne, right? Okay. And she is saying, sir, my measurement of the same object is 19.8. So all of them have error, right? So now think about it. What is the error in the first measurement? Delta A1. True value and measured value. Difference of these two things is 20.1 minus 20, which is 0.1 centimeter, right? True value minus measured value. So it comes out to be 0.1, right? Second, in the second measurement, what is the value of this thing? It is 20.2 and 20. So we can say that true value minus measured value. So let's say 20 minus 20.2, right? So see that the value comes up to minus 0.2. But should we take this minus? Answer in the chat box, right? If I'm saying that absolute error is difference of true value and the measured value, right? So 20 is the true value, 20.2 is the measured value. The difference comes out to be minus 0.2. Should I take this minus or should I drop it? We can say that absolute error is the magnitude, not the whole thing. Magnitude, only the magnitude, right? Magnitude is, how will you write the magnitude of anything? Magnitude of A is always positive, right? So be it plus 5 or minus 5, magnitude is only 5. Plus and minus doesn't matter. So we see that magnitude is magnitude of this difference. Magnitude of this difference we have to take, right? So this plus and minus doesn't matter. We have to drop that. Plus and minus doesn't matter. We have to drop that. Is that clear? So magnitude of difference between the true value and the measured value is the absolute error. Many kids do this mistake, and many kids have done it, right, in the board exam when they are asked for 1 mark, right? What is the absolute error in this one? 19.8, and they said the absolute error is minus 0.2, right? So you see that minus need not to be there because it is the magnitude of the difference between the true value and the measured value. Okay, all right. So the third one, for the third one, what will be the absolute error in the third measurement, my dear kid? So we can say that in the measurement of Pinky, right, what she has measured, right, 20 minus 19.1, so it is plus 0.1, right? And in the fourth measurement taken by Susan, so we can say that 19.8 and 20, the difference comes out to be 0.2, right? So these are the errors in the individual measurement, right? Very good. Okay, so it is always positive, right? It is always positive. I believe the idea is very, very clear, right? Simple, hai? Right? It is very simple. So let's continue. Let's continue with this idea, right? So yeah. Now the next thing is mean absolute error, right? Mean absolute error, right? So what do you mean by mean absolute error? As the name suggests, it is the mean of all the absolute errors in all the measurements that you have taken, right? So my dear kids, in the previous example, 4 kids took the measurement of the same quantity and 4 kids got these values of errors in their measurement, right? So out of all these errors, right, for this sample size, what is the mean absolute error of all the measurements, right? Let's say that these 4 kids have measured it the same thing, right? So what is the mean of their absolute error? So mean of their absolute error will be mean of their absolute error will be, what will be the mean absolute error, my dear kids? We can say that just add all the absolute error and divide by the number of measurements you have taken. So here I have taken 4 times measurement, right? So I will add all of them and divide them by 4. I will add all of them and divide them by 4. So delta A1 plus delta A2 plus delta A3 plus delta A4 by 4. So in this situation, you see that in the absolute error, we only have to take the magnitude. So 0.1, 0.2, 0.1, 0.2. So you just add it up, right? Divide that by 4. So that will give you the answer, right? I hope the idea is very, very clear. Any problem in this part? Very simple. Yes or no? Till now we are talking about extremely simple stuff, right? Very good. Very good. Priya, clear hai? Okay. So I hope the idea is very, very clear, right? So this is the idea of mean absolute error. This is the idea of mean absolute error. Now let's talk about the next one, relative error or fractional error, relative error or fractional error. So the relative error or the fractional error of measurement is defined as the ratio of mean absolute error to the mean value of quantity measured, right? My dear kids, sometimes we don't know the true value, right? Let's say that here I have this, let us say, remote, okay? And on top of this remote, no measurement is written that how long this remote is. What is the length of this remote? It is not written anywhere, for example. So what is going to happen? How do we get the true value, right? Where is the true value? So let's say that 4 kids are measuring it. First kid is measuring this remote and telling that this remote is 10.1 centimeter long. Second kid is measuring, it is saying that it is 9.8 centimeter long. Third kid is measuring, it is saying 10.2 centimeter long. Fourth kid is measuring, it is saying 10.3 centimeter long. Fifth kid is measuring, he is saying that 9.9 centimeter long, right? All these kids are giving different values. So what will be the true value, right? When you are going to calculate the error, which value should be taken as true value? My dear kids, out of all the measurements you have taken, just take mean of all the measurements, right? Mean of all the measurements. So how will you take the mean of all the measurements? My dear kids, mean of measurement will be, right, 10.1 plus this plus this plus this, just add it up. 10.1 plus 9.8 plus 10.2 plus 10.3 plus 9.9 divided by 5, right? So that will give you the mean value, right? It could be around 10.1, 10.2, whatever, right? So my dear kid, mean of all the measurement is taken as the true value, okay? That will be taken as the true value, all right? That will be taken as a true value, right? So when you don't know the true value, what you can do is, when you don't know the true value, what you can do is take multiple measurements, right? And then the mean of those measurements can be treated as a true value of the thing, right? Okay, all right, all right. Mean of those things can be taken as a true value. So once you know the mean of measurement, right, and you know that let's say the mean, let's say I'm not calculating it, let us say that it comes out to be 10.2, right? Okay, this is the mean value. And now what I will do is, I want to talk about the fractional error in each one of them. I want to talk about the fractional error in each one of them, okay? So how will you do that? My dear kids, fractional error in each one of them can be calculated just like that. So in the fractional error or the relative error in the first measurement. So first of all, tell me, it is the ratio of mean absolute error to the mean value of the quantity measured. So mean value of the quantity measured is this, right? And mean absolute error, how will you know that? What will be the mean absolute error? We can say that true value is 10.2. First measurement is 10.1. What will be the error in the first measurement? Delta 1, delta A1, absolute error of the first measurement, difference of these two. 10.2 minus 10.1, 0.1. Absolute error of the second measurement, A2 is 9.8. True value is 10.2. So just take the difference. 10.2 and 9.8, 0.4. Absolute error of the third measurement, 10.2 and 10.2. So it is 0, right? Absolute error of the fourth measurement, 10.3 and 10.2, it is 0.1. Absolute error of the fifth measurement, 9.9 and 10.2, let us say it is 0.3, okay? So you see that these are the absolute errors of all the measurement. So what is relative error of fractional error? It is defined as ratio of mean absolute error to the mean value. So you see that absolute errors you have calculated, mean absolute error will be, just add them all up, right? Add them all up. Mean absolute error will be, just add them all absolute errors, 0.1 plus 0.4 plus 0 plus 0.1 plus 0.3 divided by 1, 2, 3, 4, 5 samples, right? So this is the mean absolute error, right? So you take the mean absolute error and this is the mean value, just divide them and you have the ratio, right? Let's say mean absolute error comes out to be 0.1 and 0.4, 0.5, 0.5 and 0.1 again 0.6, 0.6 and 0.3 is 0.9, right, divided by 5, okay? So it is 9 by 50. So this comes out to be mean absolute error. So you see that mean absolute error is there, right? So what you need to do is, you can say that take the ratio of these two things. Hello. Am I audible right now? Am I audible right now? All right. Am I audible right now? All right. Okay. Thank you, Pinky. I believe the idea is very, very clear. Right. Let's continue. Okay. Let's continue. Right. The next thing is called as percentage error. The next thing is called as percentage error. So how would you define percentage error? I believe till now we have understood the relative error. Once you know the relative error of any measurement, right? Once you know, multiply that by 100, and that will be the percentage error of that particular quantity. Fractional error represented in a percentage format is the percentage error, right? Fractional error represented in the percentage format is the percentage error. I believe the idea is very, very clear. Yes, Nishant. Okay. So let's continue. Now we can talk about the combination of error. So far what we have seen, what is the meaning of error, right? And how many types of error do we have, right? How many types of error do we have? This is the second thing we have seen, that part as well. And then the next part is combination of error. The next part that we have to talk about is combination of error, right? So what we do is, think about it. Sometimes, let's say we are measuring two things. Let's say that okay. So let's say that we have this arrangement, right? So what is happening? We have this arrangement. This is an object, right? I want to make a device, right? And this bulb and holder will be a part of that device, let's say, right? So what is happening? I have connected this thing. This is the base, right? And this is the top of it, right? Now, I want to measure what will be the total length of this arrangement, right? I want to fit this whole thing inside a let's say cover, right? I want to fit this whole thing inside a cover, right? And let's say that while designing the cover, I have not measured it. Think about it. Let's say I'm making a cover like this and I want to cover the whole thing like this. So you see that if I'm not taking the measurement properly, the whole thing might not fit inside the cover. Yes or no? Right. So right now what we need to do is, right, when I am taking the entire measurement, right, I'm measuring this one and I'm measuring this one, right? While measuring the base of this thing, the holder part of this thing, I encountered some error. While measuring the bulb length, I also encountered the error, right? I made an error of delta L1 in the measurement of this part. I made an error of delta L2 in the measurement of this part. So now think about it. Can I say that the design of cover should be done in such a way that the total error is encountered already, right? Total error is considered already. Think about it. While in the measurement of this thing, I have encountered an error of 0.1 centimeter, right? In the measurement of the top part, bulb part, I have encountered error of 0.2 centimeter, right? So can I say that there is a possibility of this whole arrangement being off from the total actual value, right? And I have to design the cover in such a way that those total error can be considered as well. Yes or no? Right? I cannot design the cover based on the true values. Yes or no? I cannot design the cover based on the true value. And this is why the particular concept becomes very, very useful. Error in sum of difference. Think about it. Many times in engineering, right, we encounter a situation when we want to design something, right? Let's say that I have an element. That element has a length delta. That element has a length L1, right? That element has a length L1. Okay. And now I want to add another element to it. Okay. I want to add another element to it. The length of this element is L2, right? Now what will happen? Let us say L1 and L2, this entire arrangement I want to measure, right? But the problem is, let's say that Pinky is measuring the first part, and let's say Nishant is measuring the second part, right? Okay, so when measuring this part, in the measurement of L1, I encountered an error of delta L1, and Nishant is measuring L2. He said that while measurement of the second part, I encountered an error of delta L2, right? Okay. So instead of measuring L1, Pinky is measuring L1 plus or minus delta L1, right? And while measuring L2, this thing, Nishant is measuring L2 plus minus delta L2. Yes or no? Is that clear? Right. And now think about it. Let's say that this entire combined arrangement, I have to fit somewhere, right? So think about it. Should I keep a cavity? Think about it. Let's say this is the arrangement, right? Think we have to be very, practical about everything, right? Which is why we are learning science. You see, right? Let's say this is the box, right? And this is an object that we have to fit inside the box, right? This is an object, it's a Vernier caliper, we want to fit inside the box, right? So I must create enough space in the box, right? So that it fit just like this, right? And this whole thing can be captured inside the box very, very easily, right? Now think about it. While making the box, if I'm not considering the possible errors in the measurement of this object, I might create a smaller box and this particular thing will not fit inside it. Yes or no? Let's say that the actual length of this part is 10 centimeter, right? And I said that if somebody is measuring 10 centimeter, let's say Nishant is measuring that this part is 10 centimeter long. So make sure that the box width is 10 centimeter or slightly more than that, otherwise this will not fit inside. Yes or no? Right? I want to fit this box, this particular Vernier caliper inside the box, so I must make it wider than 10 centimeter, otherwise this will not go inside. Yes or no? Right. So now understand that Nishant is measuring this particular object, right? And he's saying 10 centimeter, but in the measurement of this distance, he can make some error because it is not straight, right? Errors are possible. He has a simple scale, and while measurement of this thing, he said that it is 10.2 centimeter, right? 10.2 centimeter. Now think about it, right? Or 9.8 centimeter. Think about it. The actual length could be 10. He measured 9.8. Okay. So what I did, Nishant is a very genius guy. I made a box which is 9.8 centimeter tall, right? So what will happen? I have not included the possible errors in the design of this process, right? And what will happen? I have created a smaller box, it will not fit inside. And this is a very simple case, right? I can be making $1 million device, right? And while the creation of those devices, if I'm not calculating the possible errors in the measurement of each and every, that will be combining together to form the eventual thing, I might lose a lot of money, right? Yes or no? I might lose a lot of money, right? There are tiny nuts and bolts, right? And I'm joining all the parts together, right? Now think about it. If I'm not what could be the total possible error, maximum possible error in the combination of these two things, right? What could be the maximum possible error in the combination of these two things? So my dear kids, the maximum possible error, delta L maximum, could be, right, when two things are added or subtracted, right, the maximum possible error in the result is the summation of individual absolute errors, delta L plus delta L2, right? Yes or no? Right, the maximum possible error in the combination, fraction of two different things is error in the absolute error of the second part, right? Making sense? Okay. Can you guys hear me properly? Right. Is that part clear with everybody? Okay. I hope the idea is very, very clear. Right. So when you are adding two things, right? Let's say that question is A is equals to B plus C, right? B and C both are measured in meters, right? Let's say that the error in the measurement of B is plus minus zero point 0.2 centimeter. Error in the measurement of C is plus minus 0.3 centimeter. What could be the maximum possible error in the final measurement, right? What could be the maximum possible error in A? So my dear kids, the maximum possible error in A would be plus minus error in the first part plus error in the second part, plus minus 0.2 plus 0.3. I hope the idea is very, very clear, right? So it is 0.5. Is that clear? Right? Okay. Okay. Right. Let's continue. Errors in the product or division. Now what is happening? We found that mathematically when we are taking the product of two different physical quantities, right? And we are encountering the errors in the measurement of each one of them, right? Let's say that we are measuring two physical quantities. Okay. Let's say A is a product of B and C, right? In the measurement of B, you have encountered an error, right? Delta B. In the measurement of C, you are encountering an error, delta C. Let's say that Nishant is measuring B, Pinky is measuring C, right? Nishant and Pinky are the hero of the class today, right? So Nishant is measuring B, Pinky is measuring C, right? And in the measurement, make an error. Whatever error he had made is delta B. In the measurement of C, Pinky can made an error, and the error she had made is delta C, right? So how are these errors going to relate with each other? Now think about it. Let's say that in the result, due to all these errors, the result will be errorful as well, yes or no? And in the result, the error is delta A, right? In the result, the error is delta A. So what will be the relation between these errors in the product or division? If it is A is B into C or A is B upon, what could be the relation between the errors of individual quantities, right? So we can say that in this situation, in the case of product or division, absolute errors are not related directly, relative errors are added directly, right? So we can say that relative error in the result, delta A upon A, is summation of relative error in this plus relative error in this. Okay. I hope the idea is very, very clear, right? Okay. I hope the idea is very, very clear. All right. Any problem in this part, my dear kids? When two quantities multiplied or divided, right, their absolute errors are not directly related. Their relative errors, however, are related, right? There are two quantities that you are multiplying. Then the relative errors are added to give the relative error in the final quantity, right? Okay. All right. So let's talk about the next one. Error in the quantity is raised to some power. Let us say that A is equals to B square, right? This is written. A is equals to B square or B cube, right? And let's say that one of you kids are measuring, right, B. The value of B is measured by one of you kids, okay? Just a second. The chat is not opening for me. Just a second. Let me see the chat and read the name of one of you. Yeah, now it is good. Okay, okay, right. So now understand that. Vivek, all right. So let's say that Vivek is measuring the value of B, right? And according to the formula, A is B square. What is that? A is equals to square of B, right? According to this formula, A is the square of B, right? Now what is happening, my dear kids? Can I say what will, let's say the error encountered in the measurement of B is delta B, right? So due to this error, some error, the result will be errorful as well, right? The result will not be actual result. There will be some error in the result. So how, let's say the error that you get in the result is delta A, right? So my dear kids, if A is equals to B square, it is written right now. And in the measurement of B, the error encountered is delta B. So what will be the final error in the result? That's what we are talking about. Now think about it. In the previous page you have just read, you have understood, if two quantities are multiplied or divided, their relative errors are added to give the relative error of result, right? Now understand that we can write B square as B into B, right? So you see that B and B are multiplied to give you the final value, right? So what will happen? In the measurement of B, the error encountered is delta B, right? In the measurement of B, the error encountered is delta B, okay? So what will happen? How is delta B related to the final result? We can say in the product, the individual absolute errors are not related, relative errors are related, right? So the relative error in the result, delta A upon A, will be the relative errors of things being multiplied, delta B upon B plus delta B upon B. Because we had B square, which is why we multiply 2 times, and what will happen? We will have 2 times delta B upon B, right? You see that relative error in the result, is fractional error of the result is 2 times fractional error of this thing, right? 2 times of fractional error of this thing, because the power was 2, which is why we have this 2 over here. If the power was 3, we would have B into B, right? Delta B upon B plus delta B upon B plus delta B upon B. So here we would have 3 times delta B upon B. If the power was n, if the A is equals to B to the power n, similarly B into B into B into B n times we can write, and the error in the result, delta A upon A, will be n times delta B upon B. Is that clear? Any problem in this part? Right? Right, very nice. Okay. So whatever power is there, it will become coefficient, right? So see that in the case of power, right, when there is a quantity raised to some power, and what you have done in the measurement of that quantity, you have done some error. So what will be the error in the result? So we can say that the relative error in the result is power. Power will become the coefficient, right? So power will become the coefficient, right? And into the absolute error, relative error of the quantity which is measured, right? Now, this is very, very useful, and it is used in multiple good numericals, right? There are a lot of good numericals you will have in your upcoming test exam in your school, right? In a lot of competitive exams and in class tests, wherever you are studying, everywhere you will have questions based on this concept, right? So let's understand that. Let's understand that. Here is a question. Here is a very, very important question, right? Read the question, my dear kids, and try to solve it. The question is like this: A is equals to B square C upon D cube. Okay. Now it is given that the relative error or the percentage error is given, right? A depends on the final value. A depends on B, C, and D, right? To get the value of A, you have to measure B, you have to measure C, put it all over there, right? Put the values of B, C, and D, and you will get the final value of A, right? But my dear kids, what happened? Pinky in the class is measuring the value of B, and she is making an error in the measurement of B, right? Instead of B, she measured something extra, right? She made an error of delta B in the measurement of B, right? And she said that, sir, in the measurement of is saying that in the measurement of B, I am encountering 1% error. So delta B upon B into 100, that is the percentage error of B. That is given as 1%. Now, Vishal is measuring the value of C, right? Vishal is measuring the value of C. Okay. Vishal is measuring the value of C, and he is saying that, sir, in the measurement of C, I have made an error of 3%, right? So what is happening? It is given percentage error in the measurement of C, delta C upon C into 100 is 3%, right? And now the value of D is measured by another kid, Vivek, okay? The value of D is measured by Vivek, right? And he's saying that, sir, in the measurement of D, I have done a grave mistake. I have done a mistake of 5%, right? Okay. So that is given delta D upon D into 100 is 5%. You see that? Listen again. The value of A depends on B, C, and D, right? With this formula, okay? So you have to measure B, C, and D and put it here to get the final value, right? So I gave this task to 3 different kids, right? Pinky is measuring B, Vivek is measuring C, and Vishal is measuring D, right? So what is happening? They all are encountering some error, right? So you say that first kid is measuring and the percentage error in the measurement of B is 1%, in the measurement of C is 3%, and the measurement of D is 5%, right? So all these errors will reflect in the answer, right? So what will be the total percentage error in the measurement of A? Clear? If all the measurement have the error, the result will also have an error, right? So what will be the percentage error in the result? This is the question. What will be the percentage error in the result? Adhu, what is your name, beta? Adhu Adi? Adhu Adi? Okay. Is that clear? What will be the result percentage error in the result, right? So we can say that percentage error in the result delta A upon A into 100 is going to be, you see that power will become coefficient, right? 2 times delta B upon B into 100 plus 1 time power is 1 upon C into 100, okay? And here the power is 3, right? So power will become coefficient 3 times delta D upon D into 100, okay? All right. So see that error, percentage error in the B is 1%. So in place of this thing, you can put 1%. In place of this is percentage error, see it is 3%, right? And in place of this thing, you can put 5%, right? So just add it up. 2 into 1 is 2, 1 into 3% is 3, and 3 into 5% is how much? 15, right? So 15 and 5 is 20%, right? So in the measurement of final value, the percentage error is 20%, right? Hello, hello. Yeah. Is that clear? And Priya Darshini has already answered it 20%. Very good, Priya beta, right? I hope the idea is very, very clear. So have you understood the concept of error and combination of errors? So we have now understood the error and the combination of errors. My dear kids, what is error is clear with everybody? Yes or no? What is error is it is clear with everybody or not? Yeah. So what is the type of error? Is it clear? Yes, the type of error is also very clear. So error is cleared. The type of error is also clear. Right. The concept of error is clear. The type of error is also clear. Right. And after clearing these things, the third thing is combination of errors. The combination of error is also clear. So the concept of error is complete. The concept of error is completed, right? Okay. Okay. It is 11th. Siddharth, it is grade 11th, right? Okay. All right. You know it's the first chapter of physics, right? So grade 11. So basically, the idea is very, very clear, right? So concept of error is completed. Now we are starting the concept of dimensional analysis. You are preparing JEE Adua. Adua. So I cannot pronounce your name, beta. So you are saying that you're preparing for JEE. How should you prepare? Focus, right? Clear the concepts and solve a lot of problems. There is, right? All other way lies. Focus in the concept and practice a lot of problems. That's the only way, right? Okay, so now understand that dimensional analysis. This is the next concept we have to talk about. Error analysis is done. Now the dimensional analysis we have to do, right? So start this particular part, right? Let's start this particular part, right? Okay, everybody. So without any further delay, let us start this particular portion. Okay. Right. So in the dimensional analysis, my dear kids, we have to cover these concepts, right? We have to talk about what is a physical quantity. We will talk about units. We will talk about writing the dimensional formula of physical quantity, my dear kids. After the first chapter, first lecture, if you don't already know the rest of the chapters, right, you cannot write the dimensional formula of every single quantity right away. But as you learn as you learn a new physical quantity and the formula of a new physical quantity, with the same concepts you can start writing the dimensional formula of them as well, right? Of homogeneity, you have to understand. Application of dimensional analysis, you have to understand. Principle of homogeneity is very, very, very important, right? I cannot stress it. Application of dimensional analysis, this is also important. And limitations of dimensional analysis, this is where the concept of dimensional analysis will be over. This is the most time taking part of this chapter, right? Without any further, start the dimensional analysis, right? So what is a physical quantity? Right, understand that in physics we can measure different things, right? We can measure length of an object, we can measure mass of an object, right? So there are so many things we can measure, speed and all those things, right? So we can measure in physics, we can measure so many different things, and the quantities which can be measured by an instrument and by means of which we describe the laws of physics is a physical quantity, right? So what is a physical quantity? The things that we measure and we use to describe the laws of physics. Force is a physical quantity, speed is a physical quantity, torque is a physical quantity, all of them, right? So they are physical quantity, and every physical quantity will have two parts, right? For example, let's say the length of an object, the length of this remote is 22 centimeter, right? The mass of this remote is 100 grams. All right. So see that every physical quantity that you have measured, here you are measuring length is a physical quantity. Here you are measuring mass, which is another physical quantity. Every physical quantity has two parts, 1, 2, 1, 2. The first part is called as the numerical value, right? This is the magnitude of physical quantity. Numerical value is the magnitude of physical quantity, and second is the unit of physical quantity, right? Here, this is the magnitude of this mass, okay, and this is the unit, all right? So we can have a magnitude n and unit u, right? So every physical quantity will have two parts, numerical value and a unit, right? Every physical quantity, P for physical, Q for quantity, physical quantity. Every physical quantity will have two parts, a unit, numerical value and a unit, numerical value and a unit, right? Every physical quantity will have a two part, numerical value and a unit. Right? So there are three different types of physical quantities. All around us, we can measure three different types of physical quantities, right? The first set of physical quantity is called as fundamental quantity. The second of physical quantity is called as derived quantity. And the third set of physical quantity is called as supplementary quantity, right? What is fundamental quantity, my dear kids? The fundamental quantity is something that you have to measure directly. You cannot measure something else and calculate that quantity. For example, you know that in grade 9 that speed is so 100 meters in 10 seconds, speed will be 100 upon 10 or 10 meter per second, right? So to measure the value of speed, you did not calculate the speed directly. What you did? You measured something else. You measured distance, how much distance the particle has covered, how much time it took to cover it. So when you measured those two things, then you were able to calculate the speed, yes or no? To calculate the speed, you have to measure something else. But think about it, something else. Can you calculate, can you measure time and distance? Can you measure length of this remote? This remote is a very important object I have right now. So you see that, can you measure length of this remote by measuring time in the clock? We can say no. I have to measure the length directly. Right? Can you measure the time? Let's say how, like, what is the duration of this lecture, right? Can you get the duration of this lecture by measuring my mass, right? By measuring my height? No, right? You cannot measure anything and get the duration, the time, right? You have to measure the time directly, right? So there are some quantities that you have to measure directly. You cannot get the idea of those physical quantities, I am measuring some other things. They are not dependent on other quantities. They are fundamental quantities. On the other hand, as it is clear, quantities which are derived from the fundamental quantities are derived quantities, and then there are supplementary quantities, right? They are simply ratios, right? Ratios, right? But again, very important. Let's look at that. These are the fundamental quantities, right? We have only these fundamental quantities. You see, 1, 2, 3, 4, 5, 6, 7. 7 fundamental quantities are there, and nothing else, right? There are 7 fundamental. All other derived quantities are written in the terms of fundamental quantities. All other derived quantities are written in the terms of fundamental quantity. Is it clear? All right. All other derived quantities are written in the terms of fundamental quantities. So length has a unit meter, right? Is meter, written with the symbol M. Mass, kilogram. Time, second. Electric current, ampere. Temperature, Kelvin. Amount of substance is mole, and luminous intensity is lambda. These are 7 physical quantities which are fundamental quantities, right? All right. So let's continue. On the other hand, speed is distance upon time, right? It depends. And force is mass into acceleration, right? So to get the value of force, you need these two things: value of mass and value of acceleration, right? So yeah, it's a derived quantity, right? Supplementary quantity, it's a ratio, right? It's a, these two quantities are ratios, plane angle and solid angle. Since the ratio same thing, for example, I'll be taking ratio of let's say my mass to the mass of heavyweight champion, right? So, but in fact, my mass is in kilogram, his mass is also in kilogram, right? So what is happening? The ratio you will be kilogram upon kilogram. It has no units, right? You see that the length of this rod. Look at that. The length of this rod is 10 centimeter. The length of the other rod is 20 centimeter. The ratio of their length is 10 centimeter upon 20 centimeter. Since it's a ratio, the unit will not, we don't cancel the unit, but just to show, the ratio of length is 1:2. It will not have any unit. So whenever we are dealing with a ratio, no, it will not have any unit, right? Ratio of two same things, it will not have any units, right? So plane angle and solid angle, these are two supplementary quantities, right? So right now, plane angle is a ratio of this arc. Let's say that this is an arc and it is subtending an angle, right? Theta, right? So this theta is a plane angle subtended by this arc, right? You can go ahead and measure the length of this arc AB, right? And you can simply measure the radius of this thing, how far that arc is, right? The ratio of arc upon length, the ratio of arc upon radius, right? The ratio of arc upon radius, yeah, will become simply this thing. The ratio of arc upon radius will simply become the plane angle. So plane angle is arc, it is 10 centimeter, 20 centimeter, 30 centimeter, right? And radius is 5, 10, 20 centimeter. Centimeter upon centimeter, it will cancel out, it will not have any dimension, right? So arc upon radius, that is going to be plane angle. That is going to be plane angle, right? Now, sir, you said that the ratio has units, but since we are measuring the plane angle, and every time if we are measuring the angle and we are not assigning any unit, because it's ratio of length upon length, ideally it should not have any unit. This is why we are in a different category called supplementary quantity, right? It's a ratio, it should be unit, right? But we are giving this ratio a unit, right? So that every time we have something to say. What is the angle? 10. What is that 10, right? So we are calling that ratio with a unit called as radians, right? There's another thing called as dimension. Even if it's a supplementary quantity and we defined a unit for it, this is a ratio. Actually, it should not have any unit. We just created a different category for this ratio and we assigned a unit, a radian, right, for this ratio, but it is dimensionless, right? So if they're asking, give us a quantity which has unit but no dimension, both the supplementary quantity have a unit. We have assigned them a unit, right? but they don't have any dimension because ultimately they are ratio, length upon length, it will not have any dimension. Right? Solid angle. Solid angle is, the plane angle is subtended by an arc of certain length. Solid angle is subtended at the center by some area, right? You see that if you have a body like this, right? So we have a dimensional body, right? If I take a small area on this body, right? What you can say, if I take a small area on the surface of this body, right? And at every point I join with the center, right? Every point I am joining with the center. So at the center, I will be making a small angle, right? If I take a bigger area on the surface, that angle subtended will be bigger, right? And it will look like this. It will look like this, right? You see, I am taking a surface, right? And that surface is making a subtending an angle like this. So that angle, this angle is called as solid angle, right? That angle is called as solid angle, right? So solid angle is subtended by area, not a single length, right? Okay. So as I said, it is also a ratio, right? Area upon square of that distance, which is square of that radius. Okay. And again, area is pi r square, and it is also r square. So here it will not have any dimension again. And ideally, it's a ratio, it should not have any unit, but we have created a separate set of quantity for them, call them supplementary quantities, right? So again, we are giving it a unit, we are giving it a unit, we are calling it steradian, right? But again, we have given them a unit, doesn't mean they have a dimension as well. Since it's a ratio, it does not have any dimension. It's a ratio of two same dimensional quantities. It will not have any unit to dimension to it, right? These are quantities independent of all other quantities and do not require the help of any other physical measurement, right? So yeah, these are two quantities, right? And we have assigned them two units, radians and steradians, right? We have assigned them two different units, radians and steradians, right? I believe it's very, very clear. Okay. Simple stuff. Beta, don't spam. Okay. So let's continue. Okay, beta. Right. So units. Yeah, these are the units. Now, writing the dimensional formula of physical quantity. Rest of the quantity is not there, but it is quantity. So writing the dimensional formula of physical quantity. See, think about it. Let's say that I am measuring the area of a body. Okay, I am measuring the area of the body. So measurement of area directly not possible. I have to measure this side and this side to get the measurement of this thing. Okay, to know the measurement area, I have to measure this length and width, right? Then I will get the area. For example, I want to get the volume, so I have to measure this, this, and also this, right? Length, width, and height, right? I have to multiply all of them, right? You see that even if the quantity, which is area, it is not a fundamental quantity, it's a derived quantity. It depends on measurement of two different things, length and width. Exactly, it's a derived quantity. It depends on two fundamental quantity, distance and time. You see that distance, measurement of distance is measurement of length of the path, which is a fundamental quantity, and time is another fundamental quantity, right? You see, these things, derived quantities depend on different powers of quantity. How many times I have to measure to calculate area, right? 1 and 2, I have to take this and I have to measure 2 times, this time and 2 times. I am measuring the length 2 times to get the value of area, right? So can I say that it depends on writing length is L. So what powers of the fundamental quantity length the area depends upon? We can say that it depends on the second power, right? Because we have to measure the length 2 times to value of area, right? So you see that the area, which is the derived quantity, depends on second power of a fundamental quantity, length. Are you getting it? Right. So the dimensional formula of area is this, right? Dimensional formula of any derived quantity tells us what powers of fundamental quantity are related with this, right? Dimension of any quantity are the powers to which the fundamental units are raised, in order to express the unit, right? So here see that length raised to the power 2. That means we are measuring the length 2 times, right? To get the value of area, right? Or it depends on the second power of the length, right? Similarly, speed depends on distance and time. Right? You see that if the distance has a dimensional formula length, right? And length of fundamental quantity of time, right? Dimensions of speed, right? These are the dimension formula of speed of any physical, be it area, speed, or any other derived quantity, are powers to which the fundamental unit must be raised, right? Fundamental must be raised in order to express the derived unit of a quantity, right? So yeah, these are the fundamental quantities. They have a certain dimension. Length has L, mass, time, current I, or in some books, current's dimensional formula is A. Temperature is K. In some books, the current's dimensional formula is theta, right? Amount of substance, mole, and luminous intensity is candela, right? So this is it. So for now, you will be using the temperature. You just use the value Kelvin. All right. So this is it. Let's continue. Right, let's try and write the dimensional formula of different things, right? So here the dimensional formula of this thing, this rod of length L is used. So this is L. What will be the dimensional formula for area? Right, dimensional formula for area is length into width. It is L2. We don't read it L square, right? We read it L2, right? And in better way, I can write it measurement of area. It does not depend on mass, right? So it depends on mass to the power 0, right? It depends on length to the power 2, and it does not depend on time, so time to the power 0. So M0, L2, T0, right? This is a better way of writing it because it helps us solving some better kind of numericals as well. This format helps us, right? For volume, it could be length into width into height, length into width into height. So they all have dimensional formula of length, right? So you see that the final dimensional formula for the volume would be L3. We will not write it L cube, it is L3, right? Or the better way of writing it would be volume is not depending on, like once you know the length and all, right? So it does not depend on mass, ML3, and does not depend on time, right? So M0, L3, T0. This is the dimensional formula for the volume, right? This is the dimensional formula for the volume, right? Now the next thing is principle of homogeneity. Now the next thing is principle of homogeneity, right? So what is principle of homogeneity, right? It is also very, very important. Okay. Okay. Moham is saying आवाज नहीं आ रही. थोड़ा आवाज बढ़ा दूं. ओके. आवाज तो बेटा फुल है. आवाज नहीं आ रही आपको क्या? मैं देख लेता हूं एक बार. Am I audible to you guys? हेलो. थोड़ा आवाज बढ़ा दूं. ओके. आवाज तो बेटा फुल है. आवाज नहीं आ रही आपको? यहाँ तो आवाज बेटा सब सही है. आप ईयरफोन्स यूज करिए, राइट? मेरे आवाज पूरी प्रॉपर आ रही है. डायमेंशनल का न्यूमेरिकल अभी होगा बेटा, अभी होगा, जस्ट फॉर 5-10 मिनट्स वी हैव कंप्लीटेड द बेसिक पार्ट, अब हम न्यूमेरिकल पर ही आ रहे हैं धीरे धीरे, ठीक है। So we are right, and just going to cover that particular part as well. So the magnitude of the physical quantity may be added together or subtracted one another only if they have the same dimension. Yeah, so principle of we are talking about, right? So understand that. Can you add the length of this object with mass of this remote? No, right? Can I add the length of this object so no. If I that I will be 5 meter, like 10 kilo potato with a rope, 5 meter rope, and I will call it 10 kilometer potato rope, right? So kilo cannot be added with meter, right? Otherwise it will become kilometer, right? So you see that together, this is the dimension of length, this is the dimension of represent different grams. They are hundred grams, and the length of this remote is only 20. Can I say that mass is more than grams by looking at the numerical value? We can say no. We cannot compare greater than or less than when they have different dimensions. One is mass, one is length. How can we compare? So we can say that two physical quantities, if they do not have the same dimension, we cannot compare them. We cannot say greater than or less than, right? If they have different dimensions. So my dear kids, two physical quantities cannot in between them if they do not have the same dimension. Yes, two physical quantities, right? Two physical quantities will not have, two physical quantities cannot be related just like that, right? If they do not have the same dimension, two physical quantities cannot be added, subtracted, have equals to sign, right? Cannot be compared with greater than or less than if they do not have same dimensions. And opposite is also true, right? If two physical quantities are shown, right? Let's say that A is equals to BC plus C cube D upon L square, right? This is written, okay? So what is absolutely true from this relation, right? Can I say that the dimensional formula of two things must be same if they are added? If they are divided, it could be different, right? You can divide two different dimensions. For example, while calculation of speed, you divided the distance and time, right? Distance is length, time is t. Two different dimensions are divided, another physical quantity is coming up. So two different dimensions can be divided and multiplied or divided, right? That can give us another physical quantity, that is allowed. But two different physical quantities added, subtracted, or they have equals to sign, greater than or less to less than sign if they have different dimensions. This is called principle of homogeneous, that homogeneity. That means two physical quantity must be homogeneous to have these relations in between them. Here, in this relation, if A is BC plus this one, that means physical. If that means this particular thing and this whole thing, they are added with plus sign. That whole thing and this whole thing must have same dimension. And look at that, there is a equals to sign, right? And if two things have equals to sign, that means they also have the same dimension. So dimension of A and dimension of this thing and dimension of this whole thing must be same. right? Otherwise, this relation will not hold true. If it is written A is equals to B plus C or B minus C, that A, B and C have the same dimension. Between B and C, there is a plus sign, right? And there is a equals to sign between A and B and in between the right side and left side. So clearly the dimension of A and the dimension of B and the dimension of C must be same, right? I hope the idea is very, very clear. Look at this thing. This is a numerical we have. A wave is represented by this relation where A, B and C are constant and T is in second and X is in meter. What will be the dimension of A, B and C? So before you solve it, just quickly tell me, right? Before you solve it, just quickly tell me, after the sign we have an angle, right? After the component we have an angle, right? Theta. So sine theta of this angle will be perpendicular upon hypotenuse. And you are measuring this length. Length. It has unit, right, radian, but it has dimension. So dimension of this whole thing is 0, right? There is no dimension to this thing. No dimension as this m0, l0, 20, right? And whenever I'm writing dimension of anything, I must use this big brackets. So we can say that the dimension of the whole thing is 0, m0, l0, t0, right? So we have to talk about the dimensions of A, B and C. My dear kids, can I say that this, and this, they have a minus sign in between? That means whatever is subtracted, they must have same dimension. Dimension of AT and dimension of BX and dimension of C, they all must be same. Yes or no? And the this is same as dimension of M0, L0, T0. Yes or no? Because there is a equals to sign over here. Can I say that? If two things are separated by minus sign, two things are separated by plus sign, two things are separated by equals to sign, greater or less than, then they all should carry the same dimension. Here AT is subtracted with BX, right? So they should have the same dimension. The dimension of this expression AT, it should be same as dimension of BX, should be same as dimension of C, and there is a equals to sign, so this is dimensionless, right? So AT in itself is dimensionless, BX is also dimensionless, C is also dimensionless, right? So what is the dimension of individual things? So let's take one by one. Take this part first. Take this part first. What 0 T0? So here X is given in meter. X is in meter. So dimension of B into dimension of X. X is in meter. So what is the dimension of meter? We can say L. And the right side is M0, L0, T0. So this L will go on the other side. Dimension of B will be M0, L minus 1, T0. Clear? So dimension of B is M0, L minus 1, T0. Or in the option, if it is not given, so you can drop 0 and 0 and you can only call it L minus 1, right? So dimension of B is L minus 1. Now the dimension of AT, as I said, this and this, the whole thing is dimensionless. So all the parts which are added are also dimensionless. So dimension of AT is same as this. Dimension of AT is simply M0, L0, T0. Dimension of A into dimension of T is time, right? It is written in T is in seconds, right? It is written T is in seconds. So clearly T is in seconds. Clearly M0 L. So dimension of A, T will go on the other side. It will be m0 L0 t minus 1 or simply t minus 1. This is the dimension of A. I hope the idea is very clear. Dimension of A is t minus 1, dimension of B is L minus 1, and dimension of C is 0 t0. So what will be the answer? We can say that what will be the answer? Answer in the chat box. Right, answer in the chat box. All right. Answer in the chat box, my dear kids. Hello. Answer in the chat box. Tell me what could be the possible thing. Option B is the right option. Right. So let's continue. Look at this question, try to answer it. The velocity of a particle as a function of time is given as this. At square plus bt plus c upon t square plus d, right? Where a, b, c and d are constant, what will be the dimension of ab upon cd? What could be the dimension of ab upon cd, right? This is something we have to talk about. So think about it, try to solve yourself, right? The velocity of a particle, velocity v in the bracket, it is written as t. That means velocity at a time t is written as, or velocity as a function of time is written as at square plus bt plus t square plus d. All right, it is written where a, b, c and d are constants, and the dimension of ab upon cd we have to talk about, right? Think about it, try to solve by yourself and tell me what could be the answer, right? We can say that with the principle of homogeneity, I will just focus on these signs, plus, equals to, and all, right? If two quantities are separated by these signs, they must share the same dimensional formula, same dimensions. So basically, the dimension of V is same as dimension of this expression, dimension of this whole expression, and dimension of this whole expression. That is same, right? So dimension of V and dimension of AT square is same. Dimension of this thing and dimension of V is same. Dimension of V is also same as dimension of BT, right? Dimension of V is also same as this whole thing, C upon T square plus D, right? And if you observe, here two things are added in the denominator. Focus. Two things are added. If two things are added, T square is added with D, right? T square is added with D. So dimension of T square has to be same as dimension of D, right? So this is the relation that we have over here between the dimensional formulas with the help of principle of homogeneity. Okay. Right. So dimensional formula for velocity is Lt minus 1. Come in the numerator, it will become minus 1 minus 2, right? So it will become Lt minus 3. So this is the dimensional formula for A. This is the dimensional formula for A. I believe the idea is very clear. Lt minus 3. Similarly, talk about the dimensional formula for velocity. It is Lt minus 1. Dimensional formula we have to calculate. For time it is t, right? So clearly t will go on the denominator, right? And as it goes up, it will become Lt minus 2, right? So this is the second part. Dimensional formula for A we know. Dimensional formula for B we know. And now the dimensional formula for D we can directly calculate from here, right? T square. This is the dimensional formula for T, right? And from here we can also calculate the dimensional formula for C. Why? Because velocity has dimensional formula Lt minus 1, right? velocity has a dimensional formula. For those kids who don't know, velocity is displacement upon time, right? Displacement is L, time is T, so velocity is LT minus 1, right? So yeah, for time square, it is D, right? So clearly, for dimensional formula for T is T square. So clearly, we can put it over here, dimensional formula for C upon, now you look at that, in the denominator, two things are added, they have the same dimension. The dimension of D is T square and dimension of T square is again T square. So the denominator has a dimension of T square, right? The denomination of the dimension of the denominator is T square, right? So T square will go over here, minus 1 and plus 2. All right. So these are the dimensional formula for A, B, C, and D. These are the dimensional formula for A, B, C, and D. Is that clear? These are the dimensional formulas for A, B, C, and D. Right? These are the dimensional formula for A, B, C, and D. All right. These are the dimensional formula for B, C, and D. Right? So just multiply it, right, and put it over here. AB upon CD. This will have a dimensional formula. Just try and calculate it, and tell me which one will be the correct answer. Right? Try and calculate it, and tell me which one is going to be correct answer. Hello? Yes. Hello? Yeah. Hello? Hello? All right. So tell me how right now. Is it loud? Is it loud right now? Priya? Pinky? Shuvdeep? Is my sound okay right now? All right. So yeah, this is it. Right. So just and tell me what could be the answer. Right. This is for you. Okay. So I'm not going to solve it. Right. I'll just give you the solution. This is what you can expect from you. T upon CD. So dimensional formula for A is LT minus 3. Right. Dimensional formula for B is LT minus 2. Dimensional formula for C is L into T only. And dimensional formula for D is T2. Just put L and L, the terms of L together and terms of T together, and you will have it. So power is cancelled out, right? So power, only one remains. We have only one. 3 and minus 2 is minus 5, right? Minus 3 and minus 2 is minus 5. And T and T3, and it will go up minus 3, 3, right? So you see that LT minus 8, that will be the answer, which is option B. Now let's move and talk about the next part. Which of the following combination of three-dimensionally different physical quantity XYZ can never be a meaningful physical quantity? So you see it is given in the Y and Z, they are all dimensionally different. Quantities will be very different, right? And over here will never amount to a meaningful physical quantity, right? Okay. Just tell me about my sound. Is it very clear or not? Okay. All right. Just tell me about my sound. Is it very clear or not? All right. I hope the idea is very, very clear. Okay. Pinky is saying, sir, thoda masti kara dijiye. What should I do? I should start dancing in the class. What should I do? I believe the idea is very, very clear, right? So X, Y, Z, they are all dimensionally different, right? Which of these relations is possible to have? We can say that, you see, two physical quantities can be multiplied, right? And they can have the same relation as the third one, right? So this can give you a meaningful physical quantity. Again, if these two are multiplied and all, it is possible. Multiplied, again it is possible, right? What is not possible, think about it, x square minus y square upon z. X square, x let's say is length, so square of length, and y let us say is time. So x square minus y square minus square of time. Can we have this minus between these two quantities because they are dimensionally different given in the question? So is this particular part possible with any possible combination? We can say no, right? This is possible in any scenario. So we will not proceed with this thing. Not proceed with this thing, right? We can say that option C is the answer, right? It will not be, right? Chalo. All right. I hope the idea is very, very clear. Let's continue. Application of dimensional analysis. So basically what we have talked about till now, we have talked about how to write a dimensional formula. We have talked about dimensional formula and how to write it, right? And then we have also seen different numericals on the dimensional formula as well. The next thing we have to talk about is application of dimensional analysis. The next thing we have to talk about is application of dimensional analysis. My voice is clear or not? Right. The next thing we have to talk about is application of dimensional analysis, right? So let's talk about it. So the first application is to convert the units, right? The first application that we have is we can use the dimensional analysis to convert the units, right? To convert the units, right? Okay, now understand that. If I say that the length of a rod is 1 meter, or I say the length of a rod is 100 centimeter, right? Is it the same thing or a different thing? Or I say the mass of an object is 1 kilogram, or I say it is 100 grams. Is it the same thing or a different thing? We can say that numerical values are different, but the units are also different, but they are representing the same thing, right? So a physical quantity always have two things, n value and u unit. So if you only change the unit, then the numerical value changes in such a way that the product stays the same. Here we have n1 and u1, here we have n2 and u2. n1, u1 and n2, u2 are representing the same thing. So if you are converting the units, only converting the units, that means n1, u1 and n2, u2 should also always be the same, right? This is the concept. So whenever you want to convert the units, n1, u1 and n2, u2 must be the same, all right? I hope the idea is very, very clear. Okay, n1, u1 and n2, u2. So basically, and now what happens whenever you are converting the unit, what will definitely not change? Here mass and it is mass. So here we can say that n1 into the same dimension of u is mlt. So let's call it m1, l1 and t1. to the power A, B, and C. Right? This is the division formula for you. M power A, L to the power B, T to the power C. The units of M, L, and T can be different. So M1, L1, and T1, right? And N2. Now in the second scenario, it is M2, L2, T2, right? Power are A, B, and C. You see that powers must be same. Powers are representing the dimension of that particular quantity, and the dimension will not change as you change the units. Power will not change as you change the units, right? So clearly N2 will be N1 M1 upon M2 to the power A, right? It will go on this side. L1 upon L2 to the power B, and T1 upon T2 to the power C. This is how you convert the units from one system to the other system, right? This is how you convert the unit from one system to the other. Very clear? Okay. Your voice is not audible. Anu, focus कर लो भाई. All right.
नहीं सर, क्लियर है आवाज तो?
आवाज क्लियर है ना?
हाँ सर।
ठीक है, फालतू कंप्लेन कर रहे हैं बच्चे. ठीक है,
हाँ,
ओके,
वॉइस इज नॉट ऑडिबल. ओके,
ठीक है, देख लीजिएगा. All right, let's continue, right? So over here, let's try and look at a situation. Young's modulus of steel is 19 into 10 to the power 9 Newton per meter square. Young's modulus express it in CGS units, right? Express it as in CGS, centimeter gram second units, right? So right now, in the SI system, the value of Young's modulus of steel is 19 to the power 9 Newton per meter square, right? You measured the Young's modulus of steel, it's a quantity, right? Which is this, right? In SI units. So force is measured in Newton in SI units, and the length is measured in meter. So in SI units, the Young's modulus comes out to be this, right? And what are we doing? We are converting it. We want to convert it into CGS units. So what will be the value? You see that? If you were just converting the length and all, we could have multiplied with something and we got the value. But right now we don't know. Like we are reading the first chapter, and I suppose you have no idea about the bulk modulus. So we don't know about anything. And since you don't know about that chapter of properties of bulk, right? So you don't know what will into CGS. Not converting again, since we are changing the numerical value. This is something we didn't about. The new numerical value. Focus. So what will be the new numerical value? So we can say that one thing is very true, sir. N1U1 must be same as N2U2, right? N1U1 must be same as N2U2, right? Numerical value in the first system is 19 into to the power 9. And what does not change upon changing the units? We can say that of a quantity the units. Yes or no? The formula will change as we change the units. Very clear, right? So what is the dimensional formula right now? So you see that dimension unit is Newton per meter square, right? Newton per meter square. Dimensional formula for Newton. Newton is the unit of force, right? You see that force is mass into acceleration, right? Dimensional formula for is dimension is m, and dimension of acceleration. Acceleration is change in velocity per unit time, right? So change in velocity is meter per second and time is t, right? So you see that for velocity it is lt minus 1 and time is t, so it is lt minus 2. Yes or no? So mlt minus 2 is the dimensional formula for force for Newton, and m square is L2. Divide it. Dimensional formula against Newton per meter square is mlt minus 2 upon L2, right? And just divide it, it will become ml minus 1 t minus 2. This is the dimensional formula for this whole thing. ml minus 1 t minus 2, ml minus 1 t minus 2. Any problem with this part? ml minus 1 t minus 2. This is the dimensional formula of this thing. ml minus 1 t minus 2, right? My dear kids, as we convert the units, the dimensional formula will not change, right? Thus the numbers will change, right? m1, l1, t1. In the SI system, mass is measured in kilograms, right? Length is measured in meters, time is measured in seconds, right? And here, numerical value in the CGS system we don't know, right? But the dimensional formula will remain same, mlt, ml minus 1, t minus 2. Mass is measured in, grams, CGS, centimeter gram second. So mass is measured in grams, length is measured in centimeter, and time is measured in seconds, right? So now you see that 19 into 10 to the power 9, that numerical value, 1 upon m2, right? So m1 upon m2 to the power 1, right? m1, m2 will come up on m2, l2, t2. So m2 comes up on this side, power is 1. L1 upon L2 to the power minus 1 and T1 upon T2 to the power minus 2. This is the value of N2, right? My dear kids, M1 upon M2, what is the unit of SI unit of mass over here? So we can say over here I can put kilograms, and in CGS system I can put grams, right? M1 is kilogram and power is 1. What is the SI unit of length? I can put meters. CGS unit of length, centimeter. Time and 19. So kilogram upon gram, I can write it 1000 gram upon gram. So gram and gram will be cancelled out. So in place of this, I can write 1000 grams. So the grams and grams can be removed. I will have 1000 and power is 1, right? In place of meter, I can write 100 centimeters. So 100 centimeter upon centimeter, centimeter will be cancelled out. It is 100 to the power minus 1. Second upon second is 1, right? So 19 into 10 to the power 9. So 100 upon power minus 1 is 1 upon 100, right? And 1000 into 1 upon 100, right? So 19 into 10 to the power 9, 1000 and 1 upon 100, right? 1 to the power minus 2 is still 1. So it is N2, right? You see that these zeros are cancelling out. So N2 is, just multiply that, 19 into 10 to the power 10. I hope the idea is very, very clear, right? So this is how you convert it into the like one system of units into the other system of units, right? This is how you can convert it from one system of units to another system of units. Any problem with this part? Right? I hope the idea is very, very clear. Hello Anamika. Hello Rifaya. Hello Study Spark. Hello everybody. So I believe everything is very, very clear till now, right? And if you have any, definitely talk about the next thing, application of dimensional analysis, right? Application of dimension analysis, right? So to establish a relation between different physical quantities. So first application of dimensional analysis is very, very clear, right? As the dimension of quantity will not change when you change the units, right? So one application could be to find the new numerical value as you change the units, right? That's one application of dimensional analysis. Second application is to establish the relation between different physical quantities, right? So you have different physical quantities and you want to relate them, right? How will you relate these different physical quantities? That's a set of challenge, right? That's another application you have, dimensional analysis, right? Another application of dimensional analysis is this, okay? How to establish the relation between different physical quantities. Now understand that. Let's say we can start it from here, right? We can start it from here directly with the problem, right? And in that way you will understand in a better way. Just a second. Hello? आप क्लास स्टॉप करेंगे तो क्या होगा? हाँ हाँ, अच्छा अच्छा, ठीक ठीक ठीक, तो मैं बोल देता हूँ एक बार, है ना? ठीक 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 ठीक. So my dear kids, I guess there's some problem in the audio. Just give me 2 minutes, right? I will fix it, right? And in 2 minutes I will come back, right? You meanwhile you can take a break, right? Just take a break. We will start from here. Five minutes, right? So right now the time is 8:13, right? If the time is 8:13, we'll come back before 8:20. Right? Come back before 8:20, right? Till then you can take some rest, right? Because the class is going on for an hour. So to give you some rest, right? Okay, so just take some rest. हाँ हाँ जी सचिन, आवाज आ रही है आपकी? तो ये क्लास रोकी गई है कि अभी नहीं रोकी गई है? All right, so I believe right now I'm clearly audible and visible, right? Okay. I hope the issue is fixed and I must be clearly audible and visible right now. Hello everybody. So took us more than expected, but yeah, I believe right now I'm clearly audible and visible. Hello everybody. Okay. Okay. So if I'm audible and visible, give me a quick yes. We can start right away with the class. Hi, hello. All right. Okay. Official Skull Gaming. Okay. All right. Sashikant. Okay. All right. Let's start right away, my dear kids. So here we are. So the next application of dimensional analysis is, so far what we have covered, we are talking about the dimensional analysis and the application of dimensional analysis right now. The first application of dimensional analysis is already very clear, right? Which is conversion of units. And then we have solved this numerical to learn how to convert the units by using the dimensional analysis, right? Now what we need to do is we have to apply the concept of dimensional analysis into another thing, right? We have to talk about how to establish a relation between different set of physical quantities using dimensional analysis, right? Okay, so there is a clear step-by-step method to do that, right? Read this problem, and with the help of this problem we will understand that how to establish a relation between given set of variables using the dimensional analysis concept. Use it. Let's area. If the area, velocity, density are base units, we are treating them as a fundamental units, and we want to talk about the dimensional formula of force, right, in the terms of these things, right? So if we are treating them as a fundamental unit, we have to talk about the dimensional formula of force in the terms of these fundamental units, right? So step one, whenever we want to talk about the dimension analysis, right, step one is always assume the relation, right? Step one, right? Let's say that the thing that we are calculating, the dimensional formula of force. So let's say that the force we want to calculate, right, it depends on the first thing, area to the power A, velocity to the power B, and density to the power C, right? And now we can further go on and calculate it, right? In the step number 2, write down the dimensional formula of each quantity, right? Step 2. Dimensional formula for force in the terms of known quantity is MLT minus 2. In the previous page, we have just calculated, right? Dimensional formula for area is LT minus A is what? Area is L square. Dimensional formula for area is L2. The better way of saying it is L2. And the power is A, right? And here the dimensional formula for velocity, V is velocity, LT minus 1. And then power is B. And D is what? Density. You see that density is mass per unit volume. So for mass, the dimensional formula is M. And for volume, it is L3. So ML minus 3 is the dimensional formula for density. So it is ML minus 3 and the power is C. Alright. And the power is C. I believe the idea is very, very clear. Right. So now you can further solve it. MLT minus 2 is, you see that on the right side we have M to the power C, L to the power, you see that L to the power 2A, L to the power B, and L to the power minus 3C. So L to the power 2A plus B minus 3C, right? And then after we have time, right? So for time we have T to the power minus B, and there is no other expression, right? So MLT minus 2, right? This is M to the power C, L to the power, from here 2A, from here L to the power B, and from here it is minus 3C, and T to the power we have only minus B, right? So this is what we have over here, right? So we want to talk about this. So this is the first step. In the first step, you want to relate this set of physical quantity. You will assume the relation is this. In the second step, you will put the usual dimensional formulas, right? And then on both sides, since they are separated by equals to sign, they must have the same dimensional formula. So on the left side, power of M is 1. On the right side, power of C is M is C. So we can say that by comparing both sides, we can get the values C is equals to 1, right? And look at that, the power of T is minus B, and power of T here is minus 2. So by comparing, minus 2 is minus B, so B is equals to plus 2, right? C is calculated and B is also calculated over here. Now, from the comparison, power of L is 1 and power of L over here is 2A plus B minus 3C, right? So just put it, 2A plus B minus 3C is equals to 1, right? So you see that C is 1, put C is 1, right? And B is 2, B is 2, B is 2, right? So 2A plus 2 minus 3 is equals to 1. So 2 and minus 3 is minus 1. So here minus 1 go on the other side, it will become 2. So A will become 1. Alright. So I hope the idea is very, very clear. So A is 1, B is 2 and C is 1. So this is the third step. By comparing on both sides with the principle of homogeneity, if two things are separated by equals to sign, by principle of homogeneity, they should have the same dimension. That means the power of M on both sides is same, power of L and power of T should also be same on both sides. So when we do that, A, B, C are calculated, right? When we do that, A, B and C are calculated. And now what we can do, we will write the dimensional formula of force, right? So look at the assumed relation. Dimensional formula for force A to the power A. A is written as small a is calculated by 1, right? So is 1, and velocity to the power B. B is 2, right? And the next thing is density. So density to the power C. C is 1. So you can write all those things. A V2 D. This is it. Right, this is how you calculate the dimensional formula, which is the option B. Option B is the correct option, right? So you see that this is another application of dimension analysis. You can relate these variables, these variables you can relate with the help of dimensional analysis, right? You can relate these variables with the help of dimensional analysis, right? Okay. I hope the idea is very, very clear, right? Now let's continue with this problem. The next thing is limitations of dimension analysis. So what's the limitation of dimension analysis? My dear kids, let's say that a pendulum is there and the pendulum is oscillating. There is a mass hanging from this rope and it is oscillating, right? So you see that this is the rope, this is the pendulum, and this is oscillating to and fro about the mean position, right? The time it is going to take in one full oscillation is 2 pi under root L upon G. My dear kids, if you start with the dimensional analysis, you can calculate that the time period is proportional to root L upon G, or you can get time period is equals to a constant time L upon G. But the value of this constant you cannot figure out. You can figure out with the help of dimension analysis what will be the relation between time, length and G, length of this pendulum. So time, period, length and the G, you can relate all these variables, but what you cannot relate or what you cannot figure out the value of constant with the help of dimension analysis, right? So we can say that dimension does not depend on the magnitude as well, and due to the reason the equation this is also dimensionally correct. You see that x is ut plus half at square, that is correct, but the constants, because these constants do not have any dimensions, so these constants and of course if you don't include this half, this equation is incorrect, but it is dimensionally correct. So if the equation is dimensionally correct, doesn't mean that equation is complete or correct itself. But the opposite is not true. If the equation is dimensionally incorrect, that equation by default is incorrect, right? But if the equation is dimensionally correct, doesn't mean if you don't include this half, the dimensional accuracy is as it is. The whole equation is still holding true. The dimension of these quantities is still same, right? So we can say that even if the equation is dimensionally correct, but since the constants are not included, the equation itself is not complete, it is not correct, right? But the opposite is not true. That means if the equation is dimensionally incorrect, that means the equation is incorrect by default. So constant of proportionality in any equation cannot be figured out, as I have already told you, with the help of principle of by any dimension analysis. And the next thing is this method is applicable only if relation of the product or ratio type, right? If the relation is of addition or subtraction type, you cannot apply the dimensional analysis to calculate or figure out the next the overall relation between those physical quantities, right? Okay. Now the next thing is devices, Vernier caliper and screw gauge. The next thing is devices, Vernier caliper and screw gauge, right? The next thing is devices, Vernier caliper and the screw gauge. So let us start talking about the Vernier caliper and screw gauge, my dear kids. Okay. So my dear kids, Vernier caliper is a very, very useful device, right? Here I have a Vernier caliper with me. Okay. So this is the Vernier caliper. Okay. It's from a decent company, right? And it can measure with decent accuracy for a really, really long time, right? You see that Vernier caliper, generally what kind of measurement tools we have? They have a single scale. They have a single scale, right? Just a second. Yeah. You see that this kind of tools we have, right? In these tools, we have only one scale, and on that scale, the markings are made, right? Whatever quantity we want to measure, let's say I want to measure this board, right? So I can just start from here, end it over here, and on that scale I will get the reading itself, right? But my dear kids, you see that if I want to make it more precise, right? For example, I want to measure the length of this thing up to certain decimal values, right? Let's say I want to measure length of this thing up to certain decimal values. Let's say this is the length I want to measure, right? I can do it with the help of a scale like this, right? And these are the markings on the scale: 1, 2, 3, 4, 5, 6, like this, right? But you see that between these, let's name them 1, 2, 3, 4, 5, 6. But you see that the object itself is not ending exactly at 4, neither it is ending exactly at 5. You see, it is ending between 4 and 5. So if I say that the object is 4 units long or the object is 5 units long, in both cases I will be incorrect. Yes or no? And I am not incorrect because of me. I am incorrect because of the precision of this instrument. Now, to make an instrument more precise, what I can do is I can further divide the available space into smaller parts, right? So I can further divide the available space into smaller parts, and now I can take it as 4.2 unit long, 4.3 unit long, right? My dear kids, it is also possible that the markings are ending in a very weird fashion, right? Let's say that over here, this is the first mark, this is the second mark, this is the third mark. Let's say the situation is like this, and the object is ending between the first and second mark like this, right? So what should I say? Object is 4.1 unit long or object is 4.2 unit long. Object is ending between 4.1 and 4.2. So what I have to do to make it even more precise, I have to further divide the available space between smaller parts. But my dear kids, there is a limit to which we can see things clearly. If I make very small markings on this scale, if I make very small markings on this scale, very close to each other, we won't be able to see them very clearly, right? We won't be able to see them very clearly, right? Okay. So for that, to avoid any confusion, what we have done, instead of using a single scale measuring tools, we are using 2 scale measuring tools, right? And they address the exact same problem, right? We had a problem of dividing this space into even further segments, right? We can achieve that part by having 2 different scale. Now understand that this is called a Vernier caliper. I also had a screw gauge, but I guess I have lost it somewhere. So here it is. You see that in a screw gauge, we have 2 different parts, right? You see that. I believe it is not very visible to you, but with the help of image and this real measuring tool, I can show you, right? So here it is. So in the Vernier caliper, we have to talk about these things. So here it is, the Vernier caliper, right? You see that this is the fixed scale or main scale. This is the main scale. It is like a usual scale. You can use it to measure things, right? Main scale. But on top of the main scale, there is another thing that slides, right? You see that? This scale is sliding over it, okay? This is the sliding scale or Vernier scale, okay? So you see that the final reading, whenever you are going to measure something, for example, I am measuring the width of this thing. So what I'll do is, I have to fix it between the jaws, right? Okay, of the caliper, and I have to press it like this so that this is completely fixed between the jaws. And now the final reading will be taken with the help of both these things, right? The final reading of the thickness of this wooden plank will be taken with the help of main scale reading plus with the help of Vernier scale reading. There will be a formula. I have to get the main scale reading. I have to get the Vernier scale reading. I have to put the main scale and Vernier scale reading in the formula to get the final thickness, right? So this instrument, with the help of using these 2 scales instead of only using one, I can get more preciseness into my measurements, right? So I believe the idea is very clear. In a Vernier scale, how many measurements you can have? In a Vernier scale, you can have two different parts, right? The first part is the main scale. The main scale is a simple part like this. There are small markings on it, and on top of the main scale, you have another sliding scale called as Vernier scale. Now, you see that there are two kind of jaws on it. So first set of jaws is it is going to use the outer dimension of anything. For example, if I have a pipe, right, or anything like this, right? So with the help of this thing, the outer jaw, I can measure the outer diameter. Okay, like this, right? So with the help of outer diameter, I can measure it like this, right? So these jaws are helping us in that way, right? But if I want to measure the inner diameter, so how will I do that? For that, I have these jaws, right? These jaws on top of it, I have these jaws. So what I'll do it, I'll insert these jaws inside, right? And then I'll simply extend it like this, right? I'll extend it like this. So this is how I will be measuring the inner diameter, right? So you see that this is a very versatile instrument. I can measure the inner diameter, I can measure the external diameter, right? And another thing, I can also measure the depth, right? I can also measure the depth. For example, what could be one instrument that I can show you to measure the depth? Okay. Oh, I have a glass, right? So let's say that I want to measure how, what is the depth of this thing? So it's a transparent thing, best thing you can see. So you see that in this Vernier caliper, I can use these different jaws to measure the outer diameter, to measure the inner diameter. These jaws will help us, right? And other than that, you see, as I start sliding the or Vernier scale on it, on the main scale, you see that as I'm sliding the Vernier scale, see something pops out on the other corner, right? You see that here I am sliding it by little amount, right? And you see that this little thing, this stick like thing that is popping out, and if I am sliding it even further, that stick is also sliding even further, right? And surprisingly, the amount of expansion, that amount of, we can say, this particular stick is sticking out, right, is same as this one, this opening, right? So I can use it to measure the depth, right? I can take it like this, right, and I can insert this stick just like this, right? And I can keep on expanding it. So here it's very sharp. So I have just 2 hands. I need 4, 5, 6 hands. All right. So I can keep on expanding it just like this. All right. You see, right? And you see that now it is a part of this thing is still inside. So you see that this thing is telling me what is the depth of this glass, right? So this is how it is helping us. We are not using right now in our class to get the value of this thing, but the measurement is still same. The depth is same. The depth, once you have measured, right, you are touching the base of this thing, right? Once you're touching the base of this thing, right, you will take the main scale reading and Vernier scale reading. You will take the main scale reading and the Vernier scale reading, put it in a formula that I'm going to show you, and you will get the depth as well in a very accurate fashion, right? Okay. Again, let me sum it up. So this is a Vernier scale, right? In the Vernier scale, you have 2 set of jaws. In this Vernier scale, the outer jaws are upside. So in this one, these are the outer diameter jaws, and these are the inner diameter jaws, right? So outer jaws and inner jaws, right? For these jaws will be helping us to measure the outer diameter. These jaws will be helping you to measure the inner diameter. This is the main scale. This is the sliding or Vernier scale, right? And this is the stem for measuring the depth, right? So yeah, all the readings will be taken up in 2 formats, 2 parts. First of all, you will be taking the main scale reading, and then you will be taking the Vernier scale reading, right? Okay. I hope the idea is very, very clear. All right. So let's proceed and talk about the next part. Okay. And let's start understanding the remaining thing. So this is the application, inner diameter, outer diameter, all of those things, right? I have shown you already. Look at this question and try to understand what is the application of Vernier scale. And we also need to know that how to calculate the least count of vernier caliper. We also need to know the least count of a vernier caliper, right? So we will calculate it over here, right? Least count of a vernier caliper. What is the smallest thing you can measure from a vernier caliper? What is the smallest thing you can measure from a vernier caliper? What is the least count of a vernier caliper right now? So all you have to do is simply believe, because it's very hard to show you in that zoomed format. So all you can see is like believing me. So what you can do is, let's say that an object is inserted between these jaws, due to which this jaw is open up by that particular amount, right? So you see that when I try to measure it, I will be having a main scale reading. You see that this is 1, right? And after 1, I have 1, 2. So 1.2 is the main scale reading, right? So in a general setting, right, if I had a simple scale, I will be saying that this object is 1.2 centimeter long. But in reality, it is slightly bigger than 1.2. So it could be 1.25, 1.27, 1.2321, like that. So how will you get the other part, right? That other part you can get with the help of this scale, the sliding scale or vernier scale, right? So the first part of the reading you will get from the main scale, and the second part of the reading you will get from the vernier scale, right? So you see that how to get the vernier scale reading, my dear kids. To get the vernier scale reading, look at the vernier markings on the vernier scale, right? And see which of these markings is exactly coinciding with any of the markings on the main scale, right? When you'll see that this mark of the vernier scale is between these two marks, it is not coinciding with any one of them. So you move on to the next one, it is still not aligning with anyone on the main scale. So you continue to keep on moving till you find, oh, I found that the first is this mark. First is this mark, right? All you have to do right now is believing, because I cannot zoom it enough and show you, right? So what is really happening, right? I can draw roughly, by the way. This is the main scale, right? And when you insert the object between the main scale and the vernier in this particular vernier scale, so what really happens? So you will get certain main scale reading. And what is really happening? The vernier scale reading over here, let's say over here I'm drawing vernier scale, right? So vernier scale markings are like this. These are the vernier scale markings, right? And these are the main scale markings that are there, like this, right? Okay, just like this. I'm drawing it randomly. So these are the vernier scale, main scale markings, right? These are the main scale markings. Main scale markings, right? And this is the vernier scale, right? So my dear kids, you will start looking at which mark is matching up first with the main scale. So I found that the first marking is not aligning with anything, second is not aligning with anything, third is not aligning with anything, but 1, 2, 3, 4, 5, fifth mark on the vernier scale is aligning with some marking on the main scale. Fifth mark is aligning with the main scale marking. Okay, so the vernier scale reading for me is 5, right? I'll be using it in the final format, but the vernier scale reading for me right now is 5 units, right? Yes or no? I have to just count and I have to look that which marking on the vernier scale is completely aligning with the main scale reading. So I found that it is like in this one, it is, let's say 1.2, 1.3, whatever marking is aligning, I will just write down that particular marking with me, right? Okay. So now what we have done is we have understood how to take the main scale reading. Main scale reading you will directly get from here, and the vernier scale reading you will get as you by looking at which number aligns first with the main scale reading, right? So yeah, so this is how you get the readings first, right? So now once you have taken the reading, how will you get the final measurement by using those two readings? Let's understand that. And to understand that, you need to know what is the least count of a Vernier scale, right? So least count of the Vernier scale can be calculated in this way, right? Let's say we have a specific situation of a Vernier caliper in which this is the main scale. Main scale has, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 markings from here, from A to B. In the main scale, we have 10 markings, right? From A to B, in the main scale, we have 10 markings, 10 gaps, right? Okay. While in the Vernier scale, in the same available length, in the Vernier scale, we have different set of markings, right? Let's say that here I am drawing the Vernier scale, right? Between A to B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10, 11, right? You see that? Or I already had the 11. Okay. So now you see that in the main scale, I have how many steps I have? You see that? Between A and B, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 steps, right? Between A to B, I have 9 steps, right? So you see, you can imagine in this way from ground floor to the first floor, right? This is the distance is same between ground floor and first floor. So if you follow these step sizes are different. You can reach following these steps, right? This is the main scale reading, right? The step sizes are different, right? While between the same ground floor and the first floor, you are following the Vernier scale, right? Between same A to B, you have more markings, right? So let's say that Vernier scale markings are like this, right? You have created more markings, more steps, and still you reached at the same step, right? So right now in this situation, let us say for a given situation of a Vernier scale, we can have different situation of Vernier scale, right? So we can say, let's say n minus 1 main scale divisions are taking the same space as n Vernier scale division. This is the minimum you have to do, right, to add some preciseness, right? N minus 1 main scale divisions are coinciding with the n Vernier scale division. N minus 1 9 main scale division are coinciding with 10 Vernier scale divisions, right? So in this space, you had 9 divisions in main scale, but in the same space, you have 10 divisions in the Vernier scale. So clearly Vernier divisions are much closer as compared to the main scale divisions, right? So this is how you have designed it, that n minus 1 main scale divisions are coinciding with n Vernier scale divisions. So clearly we can say that how big is this one Vernier scale division? We can say one Vernier scale division is n minus 1 upon n main scale division, right? Okay. All right. So what is the least count? Least count of a Vernier caliper, the least count of a Vernier caliper is a difference of one male scale division and one Vernier scale division. This is the difference. This is the least count of a Vernier caliper. Difference of one male scale division and one Vernier scale division. I believe the idea is very, very clear. So one main scale division minus Vernier scale division, you have calculated n minus 1 upon n main scale division. One main scale division could be of a centimeter, could be of a millimeter, whatever, right? So main scale division, whatever that is, will come out 1 minus n, right? Minus 1 upon n main scale division. All right. So n minus n plus 1, so 1 upon n main scale division. So yeah, so this will be the least count of this particular Vernier caliper, right? If in the given set of Vernier caliper, if in this Vernier caliper, n minus 1 main scale divisions, n minus 1 main scale divisions are coinciding with n Vernier scale divisions, right? 9 main scale divisions are coinciding with 10 Vernier scale division, then 1 Vernier scale division is equal to that many, right? So the least count is 1 main scale division minus 1 Vernier scale division, and you can calculate it like this, right? For any given Vernier caliper that is designed for you, right, you can calculate the least count for that specific vernier caliper, right? For example, if in a given vernier caliper it is shown, right, that 8 main scale divisions are coinciding with 16 vernier scale divisions. So vernier scale divisions are very close. In the same space, you have 8 markings on the main scale, but in the same space, you have 16 markings on the vernier scale. So vernier scale markings are very close, right? So one vernier scale marking, one vernier scale division is 8 by 16 or half main scale division. Yes or no? Right? So for that specific vernier caliper, what will be the least count? For that vernier caliper, the least count will be 1 main scale division minus 1 vernier scale division, right? Okay. So let's say the main scale division on that vernier caliper is of a mm, right? Each main scale division contributes to 1 mm, right? So we can say that 1 main scale division minus half main scale division. So that comes out to be half main scale division, right? So you see that on the main scale, each division is of 1 mm, but when you combine it with vernier caliper, right, the vernier caliper has a least count of half of the main scale division. Main scale division, the smallest part of that main scale was 1 mm long. So 1 mm. And this caliper, this particular caliper can measure half of 1 mm, right? This particular caliper can measure half of that 1 mm, right? So you see that we have improved our preciseness, right? We have improved our preciseness, right, without creating further markings on the same main scale. Are you getting the idea? Right? We have improved our preciseness without creating any further marking on the same main scale. All right. I hope the idea is very, very clear, right? Okay, let's move on and talk about this question. 1 centimeter on the main scale of vernier caliper is divided into 10 equal parts. 1 centimeter on the main scale is divided into 10 equal parts. If the 10 divisions of vernier scale coincide with 8 divisions of the main scale, the least count of this caliper will be. So for this specific caliper, what will be the least count? For this specific caliper, what will be the least count? Calculate that. For this specific caliper, what will be the least count? Just tell me. My dear kids, least count of a vernier caliper is simply the difference of one main scale division and one vernier scale division. One main scale division and one vernier scale division. All right. Okay. So what is one main scale division over here? It is written, from here I can do the side calculation. It is written that 10 divisions of vernier scale, 10 vernier scale divisions are equals to 8 main scale divisions, right? So one vernier scale division is 8 by 10 of main scale divisions, right? So see that, just subtract it. One main scale division and vernier scale division is 8 by 10 of main scale division, right? So you see that 1 minus 8 upon 10 main scale divisions, right? So it is 2 upon 10 into main scale division. And how big is one main scale division? It is 1/10 of a centimeter, because 1 centimeter is divided into 10 equal part, right? One centimeter on the main scale is divided into 10 equal parts. So each division is of an mm, right? So 2 into 10, and main scale division is 1/10 of a centimeter. So it is 2 by 100 centimeter, right? 2 by 100 centimeter, or 0.02 centimeter. By the way, the caliper that I have, you cannot see it, only you can believe my words, right? For this caliper also, the least count is same, 0.02, right? Because again, some kids learn this thing by heart, that for the least count of a vernier caliper is 0.1. No, it is specifically designed, right? The least count of the vernier caliper is designed for a specific use case, right? It need not to be the same in all the cases. I hope the idea is very, very simple, right? And you guys have understood this idea. Okay. All right. Any problem till now? All right. I hope we have understood this particular concept, and we can talk about the next idea. So the next concept is the concept of a screw gauge, right? What happens in a screw gauge? In a screw gauge, we have this two parts again. Just like Vernier caliper had two scales, main scale and Vernier scale. In the screw gauge also we have two scales, right? Main scale and circular scale. It is like a nut. Circular scale is like a nut, right? What happens when you rotate it? It moves forward and proceeds forward in this direction. When you turn it for in 360, when in one full rotation, it will proceed for further for a small distance, right? In one full rotation, whatever distance it proceeds further for is called as the pitch, right? How will you define the pitch? All right. So you can say that the pitch of the of this thing, the pitch of this pitch of this particular screw gauge is in one full rotation. How far that goes further, right? So let's say that if you rotate it 360 degree and it moves further by 1 centimeter, so its pitch is 1 centimeter. If you move it completely for 360 degree and it moves for 1 mm further, its pitch is 1 mm, right? So I believe the idea is very, very clear, right? We are going to calculate that as well. Okay. Now you see that there are markings on the main scale and there are markings on the circular scale, right? So clearly, we can talk about that part. How will you talk about the pitch? We can say, let's say we are rotating it 3 times, and in 3 rotations, that much part of the main scale is covered. Let's say 4 mm are covered, right? 4 mm. This circular scale is proceeding further by 4 mm in 3 rotations. So what is the pitch? Pitch is basically how further it moves in one rotation. It is moving 4 centimeter, 4 mm. It is moving 4 mm further in 3 rotations. How far will it go in one rotation? So 4, how far it is going in on the main scale upon the number of rotations. So that is telling you in one rotation, in 3 rotation it is moving for 4 mm further. So in one rotation, it will move 4 upon 3, right? That is the pitch. So pitch is nothing but the main scale reading upon the number of rotations. All right. I believe the idea is very, very clear. This is how you define the pitch. Main scale reading upon, the next thing is the main scale reading upon the number of rotations. I hope the idea is very, very clear, right? Okay, once you have calculated the pitch, now you can talk about the least count of the screw gauge. I hope the idea is very, very clear. Right. What could be the least count of a screw gauge? So least count of the screw gauge depends on 2 things. First is of course the pitch, right? The first is of course the pitch, how far it moves in one full rotation, right? And the second is the total number of divisions on the circular scale, right? How far it moves, pitch, in one rotation. And the second thing is how many markings, what is the division of the circular scale, right? So yeah. So least count is pitch upon number of divisions on circular scale. Number of divisions on the circular scale. I hope the idea is very, very clear, right? So this is the least count of the Vernier caliper, right? Okay. Okay. Acha, previously I forgot to tell you one thing, that once you have taken the reading, here I have told you that you have to take how to take the reading from the Vernier scale. So you get the main scale reading and then you get the second Vernier scale reading by looking at which point is coinciding. So once you have taken both the readings, final reading from the Vernier caliper, final reading from the Vernier caliper is main scale reading plus Vernier scale reading into least count. That's it, right? And now you can talk about the final reading from the screw gauge as well, right? So here it is. Now we can talk about we have talked about the pitch of the screw gauge. We have also talked about the least count of the screw gauge. And we can also talk about now the total reading or final reading from the screw gauge. Again, whenever you insert an object between these two parts, right, this jaw of the screw gauge, right, so you can get and you tighten it up, right, there will be a point after which you cannot tighten it further, then you start taking the reading. You see that the main scale, let's say you have a ball over here, so the main scale is open for a certain while, so it is 5 and 1 and 2, 5.2 you are getting from the main scale, and then you will get certain reading from the screw gauge circular scale, right, circular scale. So the final reading will be main scale reading plus circular scale reading into least count, right? In the case of Vernier caliper, final reading was main scale reading plus Vernier scale reading into least count. In the case of screw gauge, final reading is main scale reading plus circular scale reading into least count. I hope the idea is very, very clear, right? Okay. Now look at this question and try to solve it. A screw gauge has least count of 0.02 mm. A screw gauge has least count of 0.02 mm. So least count of the screw gauge is given 0.02 mm. All right. And there are 100 divisions on the circular scale. So number of divisions on the circular scale are given as 100. Okay. Number of divisions on the circular scale, CSS circular scale is given 100. The ratio of pitch of a screw gauge to the least count of the screw gauge is, so we have to talk about the ratio of pitch upon least count, right? This is something we have to talk about. So least count is already given. If we calculate the pitch, we can calculate the ratio. So what will be the pitch of a screw gauge, right? What is the pitch of a screw gauge? We can say from the formula, we have seen the least count is pitch upon number of divisions in the circular scale, and these things are given to us, right? Right. We have seen it. The least count is pitch upon number of divisions in the circular scale. So clearly the pitch will be least count into the number of divisions. So least count is 0.02 mm and the number of division is 100. So it will be 2 mm. This is the pitch, right? Pitch upon least count will be 2 upon 0.02. So this is 100. Option A is correct answer. I hope the idea is very, very clear. Right? So that's pretty much everything about the screw gauge and the Vernier caliper part, right? And now we can move on and talk about the next part, significant figures, right? Okay. So this is the last part of this particular chapter where we are going to learn how to talk about the significant figures, right? So the basic rules for writing the significant figure is same, right? It's very simple. The first thing is significance of non-zero. Right? If you have a measured value or calculated result and it comes out to be 102, let's say all the values that you're getting right now are non-zero. It is 135.7628, right? Like this. There is no zero in it. So all the numbers in this one are significant, right? 135.762.8, 135.7628, and there is no point. 1, 2, 3, 4, 5, 6, 7. There are 7 non-zero numbers. 1, 2, 3, 4, 5, 6, 7. Again, 7 non-zero numbers. Decimal can be anywhere. It really doesn't matter. In all of them, there are 7 non-zero numbers. So the number of significant figure is 7. Okay. Now, how will you decide the significance of 0 in different situation? My dear kids, non-zero is always significant. But 0 is significant only in specific circumstances, right? For example, if it is written 2.002035500, right? So where we have different types of zeros, right? Look at that. We have 0.0023567802, like this. So we have different types of zero again in this situation. So let's make this number slightly prettier. All right. So here we have it. We have two different examples and we want to know which of these zero is significant and which of these zeros are significant and what will be the number of significant figures in each one of them, right? So the first one is, here you see before decimal we have a non-zero number, and in this one before decimal we have a zero, right? Okay. So we need to understand this zero, these zeros are between two non-zero number. Similarly for this zero, so they are between two non-zero number. We will call them trapped zeros, right? And trapped zeros are always significant. The trapped zeros are always significant, right? Trapped zeros are always significant. So if it is written 205, so how many significant figures are there? 1, 2, 3, because 0 is trapped between two non-zero numbers. So there are 3 significant figures, right? There are 3 significant figures. I believe the idea is very, very clear. Right. Okay. And now look at that. These zeros are trailing zeros, right? Trailing zeros, zeros that come at the end are trailing zeros, right? These zeros are coming at the end of the number. They are the trailing zeros. All right. Trailing zeros. So the trailing zeros are not always significant, right? That means there is a case when they are significant and there is a case when they are not, right? You see, if there is a decimal, in that situation, the trailing zeros will be significant, right? Okay. If there is a decimal, if there is a decimal point, then in that case, trailing zeros are significant. If there is no decimal point, in that case, trailing zeros are not significant. That means if I have 5.0, so how many significant figures? 0 is significant, trailing zero. We have 2 significant figures, right? We have 5.20. We have 3 significant figures. SFB significant figure, right? But in the case of if we don't have any decimal point right now, let's say we have 50. So this 0, there is no decimal point. So here we have only 1 significant figure. If we have 520, here we have only 2 significant figure. All right. I hope that is very, very clear. Okay. Okay. And now you see that if there are zeros and before those zeros there is no non-zero number, so all these zeros are called as leading zeros. And leading zeros are never significant figure. All right. This 0 is a trapped 0. These are trailing zeros after decimal. So they all are significant over here. But right now, you see, these are leading zeros and they are never significant. So let's summarize. Trapped zeros are always significant, right? Trapped zeros, zeros between non-zeros. Trapped zeros are always significant. Leading zeros are never significant. And trailing zeros are significant only when they are coming after a decimal point, right? So yeah. Yes. I hope the idea is very, very clear, right? And now, rules for rounding off. Now understand how this is the last thing. Rules for rounding off, right? There is after that there is accuracy and precision as well. So rules for rounding off. So how will you round off something? So you see that if I have 1.235, and let's say that after this point, let's say after after one step after decimal, one digit after decimal, I have, this is the cutoff digit. Everything I have to drop. I have to drop from here. So this is the cutoff digit, right? And after the cutoff digit, this part I have to remove, right? This part I have to remove. Okay, right? So what will be the rounded off number? So if the part which is removed, this, look at the digit after the cutoff digit. So this is the cutoff digit, cutoff number. After the cutoff number, if the number is more than 5, then the previous number will be increased by 1. Otherwise, it will remain as it is. So here the number is 3. It will remain as it is. But if there was a case when it is, let's say 1.265, and this is the cutoff digit, we have to remove the remaining part. So in that case, the previous value will be increased by 1. So it will be 1.3. Okay. Now what is happening? If I have a number which is neither less than 5 nor more than 5, it is exactly 5. Like 1.255, like this. So in that case, if this is the cutoff digit and I have to remove it, what should I do? Should I increase it by 1 or should I not increase it by 1, right? So in that situation, if the number after cutoff digit is 5, not less or more than 5, so I will look at cutoff digit, right? If it is even, if the cutoff digit is even, I will not change it. If the cutoff digit is odd, 355, and I have to remove it from here, so I will increase it by 1. It's a convention and there is no sense behind it, right? So yeah, this is one of those inorganic chemistry moments for you in physics. But yeah, that's pretty much everything, right? And now the next thing and last thing of the lecture is accuracy versus precision, right? Precision is how many close markings are available in the measuring instrument so that you can further measure it up to more decimal places, right? So let's say that the true value of this rod, the length of the actual length, the true value of this length is 20.5 centimeter, okay? 25 centimeter, or let's say that it is only 20 centimeter for simple explanation, right? Let's say that true length of this rod is 20 centimeter, right? First measurement is this 19.9 centimeter, right? Second measurement is 19.82 centimeter, right? So see that 20 is the actual length and the first measurement is clearly closer to the actual length. So we can say that first measurement is more accurate, right? Accurate. So accuracy has to do with how close the measured value is to the true value, right? So if you are closer, 19.9 is closer than 19.8 something. So it is a more accurate value. And preciseness has something to do with till how many decimal points you can measure something. So with this instrument, you had a chance to measure at second decimal place as well. So clearly the second measuring instrument was more precise, right? So this is a more precise measurement. All right. So in reality, what do you want? The best case scenario is the reading is more precise as well as more accurate. For example, if the reading was 19.92, right? So it is not only more accurate, but also more precise, because it is, you see that 19.9 is there, but 19.90, right? But this one is giving us better idea, 19.9, and there is another decimal point. So we have an instrument which can measure to a second decimal point and also closer to it. So this is accurate and precise than all these measurements, right? So this is the best case scenario. Our measurement is more accurate and more precise, right? But here we have understood that accuracy means how close you are to the actual value, and preciseness has to do with how until how many decimal places you can measure something, right? So that's pretty much everything for this particular lecture, my dear kids, right? And here we have completed each and every concept of this particular class, right? Okay. I hope you have understood everything. Piyush. Hello, Piyush. Okay. How are you? Chalo. All right. So the class was slightly longer than 3 hours. I guess I have to teach you for 3 hours or so, but I hope you have understood each and everything, right? Okay. I guess we have understood the concept of error analysis, the concept of dimensional analysis, the concept of Vernier scale and screw gauge, concept of significant figures and rounding off, right? And accuracy versus precision. So all those things we have covered in this class, and this is definitely going to help us in scoring you well in the upcoming exams, right? So, and in this way, if we keep learning now, our basic concepts will be rock solid, right? And then we all that is left with us is practice more, right? And if you keep on doing that, my dear kids, you will definitely do much better in your life and in all the exams that you're going to give, right? So I'll keep this class till here only, right? Okay. Bye bye, Piyush. Thank you. Right. Okay. Bye bye, Moonlight. Bye bye, Smarty, Sidhu, Kumari Pinky. हम भी हैं. Okay. All right, everybody. Bye bye. Right. I'll see you there in the next class, my dear kids. Till then, take care. Bye bye. Every week, Monday, 6:30, we are going to do another physics lecture of grade 11th, right? And gradually, if you follow now, 4 weeks from now, that is 1 month, there will be a set of kids who don't know the 4 chapters, right? There are only 14, right? So there will be a set of people like in 2 months, you will have half of the syllabus of grade 11th, right? And yeah, that's an advantage that you will have if you just, continue in a better way. All right, I'll keep this class till here only. I'll see you there in the next class. Till then, take care and bye bye.